This study examines weak, thermonuclear X-ray bursts from the accreting millisecond X-ray pulsar SAX J1808.4-3658, focusing on two events observed with the Neutron star Interior Composition Explorer in 2019 and the Rossi X-ray Timing Explorer in 2005. These bursts occurred shortly after the onset of outburst, with the 2019 burst happening 2.9 days after fresh accretion began and the 2005 burst occurring 1.1 days after the first indications of fresh accretion. The peak burst bolometric fluxes were measured at 6.98 plus or minus 0.50 times 10 carat 9 and 1.54 plus or minus 0.10 times 10 carat 8 erg cm carat 2 s carat 1, significantly lower than the peak flux of the brightest, helium-powered bursts observed from this source. Spectral modeling was used to estimate accretion rates and accreted columns at the time of each burst. The 2019 burst had an accretion rate of approximately 1.41.6 times 10 carat 10 m_year carat 1, and an accreted column of 3.95.1 times 10 to the 7 gram cm carat 2. In contrast, the 2005 event had a similar accretion rate but with half the accreted column of the 2019 burst. The low accretion rates, modest columns, and evidence for a cool neutron star in quiescence suggest these bursts are triggered by thermally unstable CNO cycle hydrogen burning. The post-burst flux level in the 2019 event appears offset from the pre-burst level by an amount consistent with quasi-stable hydrogen burning due to the temperature-insensitive, hot-CNO cycle, further suggesting hydrogen burning as the primary fuel source. This provides strong observational evidence for hydrogen-triggered bursts. The study's findings are consistent with previous theoretical modeling, which identified three bursting regimes based on the mass accretion rate. At higher accretion rates, a helium shell grows via accretion and thermally stable CNO cycle burning that converts some of the accreted hydrogen to helium. At lower accretion rates, a thick helium layer accumulates, leading to the ignition of a thermonuclear runaway. The lowest accretion rates result in the accumulation of a thick layer of hydrogen, which then undergoes a thermonuclear instability. The observed bursts are likely triggered by hydrogen burning, as opposed to helium burning, due to the low accretion rates and modest columns observed. This study contributes to the understanding of thermonuclear X-ray bursts and their relationship with accretion rates, providing valuable insights for further theoretical modeling and experimental investigations. The triple alpha instability in the shell of an accreting neutron star can lead to thermonuclear bursts. These bursts can be either mixed-age, He bursts or pure helium bursts, depending on the accretion rate. Mixed-age, He bursts occur when hydrogen is present in the shell, allowing for the rapid proton capture process to occur, resulting in longer duration bursts. Pure helium bursts, on the other hand, occur when the helium burning is initiated in a pure helium shell, resulting in a rapid, intense energy release. At low accretion rates, temperatures in the accumulating shell may be low enough that steady CNO hydrogen burning essentially switches off, but can proceed in the unstable, temperature-sensitive regime. This can lead to unstable ignition of the hydrogen in the accumulating shell, potentially producing a prompt, mixed-age, He burst or fuel accumulation until helium ignition occurs. However, observational evidence for this hydrogen ignition regime is limited. One observed case of triple, short recurrence time, SRT, bursts from the high inclination, eclipsing source X00748676 has been reported, with the initial bursts potentially attributed to either helium-triggered, mixed-age, He bursts at moderate accretion rates or hydrogen-triggered bursts at lower accretion rates. A theoretical mechanism for SRT bursts has been outlined, involving opacity-driven convective mixing that transports fresh fuel to the ignition depth. This paper presents a study of an apparently rarer class of weak X-ray bursts observed from SAX J1808.4-3658, arguing that they show the hallmarks of being associated with the hydrogen ignition regime. The source, an accreting millisecond X-ray pulsar, has been extensively observed during 10 outbursts, with a distance estimated at 3.5 plus or minus 0.1 kpc. The neutron star binary SAX J1808 exhibits two types of thermonuclear bursts: bright pre-bursts and weak bursts. Weak bursts are characterized by lower peak fluxes and fluences, and are not Eddington-limited. Observations indicate that these weak bursts occur during the initial stages of outbursts, preceding the bright bursts. This is notable, as the neutron star cools significantly in quiescence, and the unstable hydrogen-burning regime requires cooler temperatures in the accumulating layer. A weak burst observed with the Neutron Star Interior Composition Explorer, NICER, during the 2019 August outburst from J1808 is the focus of this study. NICER data and light curves of the initial part of the outburst are presented, showcasing a single weak burst. A spectral study of the persistent and burst emission is also conducted to understand the energetics and constrain the mass accretion rate in the likely accreted mass column at the time of ignition. The NICER observations of J1808 began on August 1, 2019, in response to an increase in optical flux, potentially indicating a new X-ray outburst. The data were screened using standard criteria, and cleaned event lists were produced using NICERDAS version 8. The light curves and spectra were generated using HEASOFT version 6.29c. The light curve of the outburst over approximately 20 days reveals two X-ray bursts, with the focus of this study being on the weaker first burst, which occurred at 58,704.80764 mjd, tt. This burst is of particular interest, as it provides insight into the initial stages of the outburst and the conditions that lead to the onset of thermonuclear burning. To constrain the total accreted mass from the beginning of the outburst up to the onset of the first burst in J1808, the authors model the spectrum of the persistent emission to determine its flux and then integrate it from the outburst onset to just prior to the first burst. This integral provides an estimate of the energy fluence produced via accretion, which can be converted to an accreted mass using standard assumptions for the accretion luminosity produced by the release of gravitational potential energy of the accreted matter. The persistent spectrum is found to gradually change during this portion of the outburst, with a modest hardening over time. To account for this variation, the authors measure the flux at several intervals along the outburst rise and use these measurements to estimate the flux per unit NICER count rate. They then employ simple linear interpolation and the trapezoidal rule to integrate the flux from outburst onset to the first burst, thereby estimating the energy fluence. The energy spectrum of the preburst interval is modeled using a phenomenological model consisting of disk BB, B bodyrad, and power law components, in addition to a line at 1 keV. This model is fit across the 0.510 keV bandpass, providing an excellent fit with a minimum chi2 of 117.9 for 112 degrees of freedom. The best fitting model parameters yield an unabsorbed flux, 0.120 keV, of 7.06 plus or minus 0.23 times 10 carat 10 erg cm carat 2 s carat 1, and a bolometric flux, 0.1100 keV, of 7.9 times 10 carat 10 erg cm carat 2 s carat 1. The average count rate in the fitted energy band, 0.510 keV, is 181.9 plus or minus 0.5 s carat 1, allowing the authors to estimate a flux per NICER count rate, 0.510 keV, of 4.34 times 10 carat 12 erg cm carat 2 s carat 1 counts s carat 1 carat 1 for this interval. The light curve in Figure 2 illustrates the first weak burst from J1808 in the 0.47 keV band observed with NICER, with vertical dashed and dotted lines denoting the intervals used to extract spectra for pre- and post-burst spectral modeling, respectively. The inset panel highlights the offset in count rate between the pre- and post-burst emission, with a dashed red line representing a constant value fit to the preburst level. The neutron star low-mass X-ray binary SAX J1808 was analyzed using data from the Neutron Star Interior Composition Explorer, NICER, to investigate the spectral models of its persistent emission before a thermonuclear burst and its relationship to the outburst rise. A combination of disk blackbody, disk BB, blackbody radiation, B bodyrad, and a Gaussian line component was used for the spectral fits. The results are presented in Table 1, including the hydrogen column density, nh, disk blackbody temperature, kT, normalization, norm, and power law index and normalization for the high-energy emission component. A narrow, unresolved Gaussian line at approximately 1 keV was detected in the preburst and 1 postburst interval with a significance of 4.2 and 3.5 sigma, respectively. However, this line was not detected in the spectrum extracted closest to the outburst onset and at the lowest observed flux. Excluding the 1 keV line from the spectral fits did not significantly alter the inferred flux, but its inclusion provided a better overall statistical description of the data. To estimate the outburst fluence, linear interpolation between data gaps and the trapezoidal rule were employed to integrate the total counts, yielding a persistent emission energy fluence of EP equals 7.92 times 10 to the 5 erg/cm squared. This represents the total energy associated with accretion from the outburst onset up to the initiation of the first observed burst. The total accreted mass required to produce the observed energy fluence was estimated using the equation for spherical accretion, which considers the observed, accretion-driven luminosity, LP, observed bolometric flux, FP, mass accretion rate, persistent emission anisotropy factor, Xp, neutron star mass, m, and radius, r. The anisotropy factor, Xp, represents the solid angle into which the radiation is emitted, normalized by 4 pi, with isotropic emission characterized by Xp equals 1. The accreted mass column in the local neutron star frame is expressed as Ya equals Ma, 4 pi r squared, equals Rm, T, dt, 4 pi r squared, where T denotes the time measured at the neutron star surface. This expression can be rewritten as Ya equals D squared Xp, 1 plus Z squared, Zc squared R squared Z, Fp, T, 1 plus Z, dt, equals D squared Xp, 1 plus Z squared, Zc squared R squared, Ep, where T is the time measured in the observer's frame, and Ep represents the observed energy fluence. Assuming a distance d equals 3.5 kpc and Ep equals 7.92 times 10 carat 5 erg/cm carat 2, the accreted column can be written as Ya equals 1.03 times 10 to the 7 Xp, 1 plus Z squared, Zr underscore 10 to the power of 2 gcm carat 2, where R underscore 10 is the neutron star radius in units of 10 kilometers. For a neutron star with mass m equals 1.4 m circled dot operator and radius r equals 11 kilometers, and assuming Xp equals 1, the accreted column is estimated to be Ya equals 5.12 times 10 to the 7 gram/cm carat 2. For a more massive neutron star with m equals 2.0 m circled dot operator and r equals 11 kilometers, the accreted column decreases slightly to 3.91 times 10 to the 7 gram/cm carat 2. The mass accretion rate m at the time of the weak burst onset can be estimated using the preburst flux of 7.9 times 10 carat 10 erg/cm carat 2 s carat 1, yielding m equals 2.03 times 10 carat 11 Xp, 1 plus Z cubed Zm circled dot operator year carat 1. With the same parameter assumptions, the estimated mass accretion rates are m equals 1.56 times 10 carat 10 and 1.38 times 10 carat 10 m circled dot operator year carat 1, respectively. The burst spectral evolution is analyzed by segmenting the burst light curve into intervals of approximately 500 counts using a 1/8 time bin. The resulting evolution of the bolometric flux, blackbody temperature, and blackbody radius are shown in Figure 4. The peak bolometric burst flux is estimated to be Fb equals 6.98 plus or minus 0.50 times 10 carat 9 erg s carat 1 cm carat 2, and the bolometric fluence is calculated to be 7.05 plus or minus 1.16 times 10 carat 8 erg/cm carat 2, using trapezoidal numerical integration. The burst luminosity is defined as Lb equals 4 pi d squared Xb, where Xb characterizes the anisotropy of the burst emission. Adopting Xb equals 1 and d equals 3.5 kpc, The total energy released during the burst is estimated to be 1.03 times 10 to the 38 ergs. The physical scenario and interpretation of the weak X-ray burst in J1808 are discussed in the context of nuclear burning on neutron stars, with surface effective temperature constraints in quiescence and theoretical results suggesting a core temperature for J1808 in the range from 7.2 to 7.7 times 10 to the 6 K for neutron star masses between 1.4 and 2.0 m circle dot operator. Hydrogen-triggered thermonuclear bursts from SAX J1808 are characterized by thermally stable cycle hydrogen burning, primarily driven by compressional heating. This regime is less efficient than hot-CNO cycle burning in the stable burning regime. To maintain a stable hydrogen-burning shell, Fujimoto et al. 1981 estimated the required accretion rate, MIST, B, as 2.7 times 10⁻⁻10 m circle dot operator year⁻⁻1 for a neutron star mass and radius of 1.41 m circle dot operator and 6.57 kilometers. With a more typical radius of 11 kilometers, this rate increases to approximately 3 times 10⁻⁻10 m circle dot operator year⁻⁻1, equivalent to 0.0167 med. In contrast, Cumming, 2004, quotes a value of m0.01 med for stable, hot-CNO cycle hydrogen burning, while Cooper and Narayan, 2007, found that hydrogen-triggered bursts occur at low accretion rates, specifically 0.003 med. The estimated accretion rate at the time of the weak Neisser burst, m approximately equals 0.0077-0.0087 med, falls within the range consistent with Fujimoto et al.'s 1981 case 3 shell flashes, where the accumulating layer remains cool enough for CNO hydrogen burning to proceed in the temperature-sensitive regime. Only about 1–2% of the hydrogen would be burned prior to ignition in this regime. The estimated total column of matter accreted at the time of the burst, 3.91–5.12 times 10 to the 7 grams cm², and its total energy fluence, 1 times 10 to the power of 38 erg, suggest that the column would be ignited at a temperature in the range of 4–5 times 10 to the power of 7 K upon ignition. The unstable burning would quickly heat the layer, raising the temperature to at least that at which the CNO energy generation rate saturates. Fujimoto et al. 1981 estimate that only a small fraction, delta X, of the hydrogen needs to burn to raise the temperature, specifically delta X approximately equals 0.002 for a temperature change of 10 to the power of 8 K after ignition. Two subsequent paths have been described in the literature. Either the ignition column remains small, requiring additional accretion and/or an increase in the helium fraction before helium ignition, or a temperature increase of a few 10 to the power of 8 K would render the shell unstable to helium ignition, promptly producing a mixed He burst. The measurement of the burst fluence enables the estimation of the fraction, FH, of accreted hydrogen needed to burn to produce the observed energy. For an energy release of 6.4 times 10 to the 18 erg G⁻⁻1, approximately 1.6 times 10 to the 19, 1 plus Z, G of hydrogen would need to burn, corresponding to a column of 1.05 times 10 to the 6, 1 plus Z, G cm²-2. The neutron star system 4U-160852 was observed to exhibit a weak X-ray burst characterized by a low energy release and short duration, suggesting a possible, hydrogen-only, flash. Calculations using the estimated accreted column and observed energy release indicate a mass fraction of hydrogen in the accreted fuel between 0.04 and 0.06. However, this value represents a lower limit, assuming that the total accreted column produced only one such burst and neglecting the effects of sedimentation, which would likely reduce the mass fraction further. Following the burst, an offset was observed between pre- and post-burst flux levels, indicating potential ongoing hot-CNO cycle burning. Spectral analysis of the post-burst data, using the same model as for pre-burst and persistent emission intervals, revealed that the post-burst spectrum cannot be fit using the pre-burst spectral shape, suggesting an additional spectral component in the post-burst interval. Subtracting the preburst spectrum from the postburst spectrum yielded a soft thermal spectrum characterized by a blackbody with kT equals 0.51 plus or minus 0.02 keV, normalization of 82.5 plus or minus 12.0, and a bolometric flux of 6.1 plus or minus 0.2 times 10 to the 11 erg cm squared s⁻1. Corresponding to a luminosity of approximately equals 8.9 times 10 to the 34 erg s⁻1 at 3.5 kpc. Estimating the hydrogen burning luminosity, assuming stable burning at the same rate as accretion, resulted in a value of approximately equals 4 times 10 to the power of 34 erg s⁻1, a significant fraction of the measured offset, suggesting that the observed offset could be due to ongoing hot-CNO burning. Furthermore, using the saturated hot-CNO burning rate, the energy production rate associated with hot-CNO burning was estimated to be LCNO approximately equals 6.4 times 10 to the 34, ZCNO, 0.01, erg s⁻1, where ZCNO represents the abundance of CNO catalyzing elements. The authors of this research paper delve into the weak thermonuclear burst observed in SAX J1808. A low-mass X-ray binary system. They propose that the burst is triggered by the ignition of hydrogen at the base of the accreted fuel layer, leading to hot-CNO burning. This interpretation is supported by the observed thermal nature of the spectral excess and its temperature of approximately 0.5 keV, similar to that seen during the weak burst. The authors reference previous studies, such as Peng et al. 2007, which reported enhancements in CNO element abundances by factors of 2 to 5, depending on the accretion rate. They suggest that the two-zone model of Cooper and Narayan, 2007, may not adequately track the fast, initial hydrogen burning phase, but better predicts the longer timescale, thermally stable burning. They argue that more detailed, radially resolved, and perhaps multidimensional calculations are needed to accurately track the rapid hydrogen ignition phase. The authors also discuss the possibility of missed bursts, given the modest on-source coverage of NICER observations. They argue that, based on estimates of the size of the accreted column and theoretical estimates of the hydrogen ignition curve, only a few such bursts might have been missed. They set a minimum combustible column for hydrogen ignition, using the ignition curve in Cumming, 2004, as a guide, and estimate that not more than about 5 such bursts could have been produced. An analysis of a similar event observed with RXTE during the 2005 outburst is also presented, which shows qualitatively similar properties to the weak NICER burst. The authors find that this burst reaches a peak bolometric flux about a factor of 2 greater than the NICER burst, with a peak blackbody temperature about 25% larger. Overall, the authors suggest that the weak NICER burst and postburst flux offset are consistent with the onset of a hydrogen-triggered shell flash in the cool, temperature-sensitive regime of the CNO cycle. The study focuses on the 2005 outburst of the neutron star J1808, observed by RXTE and NICER. RXTE light curve data reveals a weak X-ray burst early in the outburst, followed by brighter and more energetic bursts near days 4 and 8. The first evidence of active accretion was provided by RXTE, PCA galactic bulge scan observations on May 31, indicating a persistent 210 keV X-ray flux level of approximately 3 mCrab. The X-ray burst was observed approximately 25.7 hours later, with a reported peak bolometric flux of 1.6 times 10⁻8 erg cm-2s-1 and a fluence of 1.67 times 10⁻7 erg cm-2. The persistent flux at the time of the burst was estimated to be 8.6 times 10⁻10 erg cm-2s-1. By evaluating a simple trapezoidal sum, the persistent, accretion-driven fluence prior to the weak 2005 burst was estimated to be approximately half of that estimated for the 2019 NICER event. This suggests a total accreted column just prior to the 2005 RXTE event of about half that estimated for the 2019 NICER burst, with a range of 2.0–2.6 times 10 to the power of 7 GCM- for the total accreted column prior to the 2005 RXTE event. Additional observations of J1808 were collected with NuSTAR between August 10 and 11, 2019. While these data do not cover the time of the weak X-ray burst observed with NICER, NuSTAR did catch 2 subsequent bursts. The NuSTAR light curve reveals 2 X-ray bursts, the first of which occurred 24.8 hours after the weak NICER burst, and the second occurred another 11 hours later. The persistent emission was investigated by extracting a spectrum from a 100-second window just prior to the first NuSTAR burst. The spectrum was modeled using the same persistent emission used previously, allowing for a constant cross-calibration factor between NICER and FPM-A/B of NuSTAR. The bolometric flux estimate was found to be 1.47 plus or minus 0.05 times 10⁻⁹ erg-s-1 cm². From the recurrence times between the observed bursts, the study finds the fluence due to accretion was estimated to be 1.3 times 10⁻⁴ erg-cm² and 5.8 times 10⁻⁵ erg-cm² for the 2 bursts, respectively. Converting these measurements to column depths, the study finds 8.4 times 10 to the power of 7 and 3.7 times 10 to the power of 7 g-cm², respectively. Observations of SAX J1808 revealed a hydrogen-triggered thermonuclear burst, detected as a weak X-ray burst by NICER, and 2 more energetic events detected by NuSTAR. A proposed scenario suggests that initial accretion occurs when the neutron star is cool, with low accretion rates, enabling CNO hydrogen burning in the accumulating layer at temperatures conducive to instability. When the accumulated column reaches 3 times 10 to the 7 g/cm², significant burning initiates, triggering the observed weak X-ray burst. After hydrogen ignition, the burning layer reaches temperatures permitting hot-CNO cycle burning. This heat source maintains layer temperatures for several hours, but the quasi-steady burning phase's duration cannot be precisely determined due to NICER coverage gaps. However, post-burst observations approximately 3.5 hours later showed a return to pre-burst levels. In contrast, the NuSTAR bursts were 47 times more energetic than the weak X-ray burst, with fluences of 5 times 10 to the power of 7 erg-cm² and 3 times 10 to the power of 7 erg-cm². They reached a peak blackbody temperature of 2.3 keV. Steadily increasing accretion rates significantly affect layer temperatures. Further modeling of this process will need to account for the time-varying accretion rate. Speculations regarding observed details, based on the proposed scenario, include comparisons with the 2005 RXTE event and the 2019 event observed by NICER. Given its timing relative to the outburst onset, the RXTE event was expected to occur when the accreting layer was cooler. Consequently, this would lead to a larger unstable column and increased energy, explaining why it is more energetic. These observations suggest the possibility that a preceding weak burst occurred but went undetected prior to the 2019 event. Key limitations include estimating accretion rates and accreted columns, and neutron star mass variability, underscoring the need for refined models accounting for time-dependent accretion. A study of weak X-ray bursts in the neutron star J1808 highlights the distinct environment presented by early accretion outburst evolution onto a relatively cool neutron star. This environment may give rise to weak bursts resulting from the ignition of unstable hydrogen burning within the temperature-sensitive regime of the CNO cycle. Investigations of such weak bursts have important implications for our understanding of nuclear burning in the accreted layers and thermal energy transport in these layers. By achieving complete and continuous observational coverage of the initial 45 days of subsequent outbursts from J1808, researchers may test the unstable hydrogen burning hypothesis, yielding insights into physical properties like the accretion rate and the thermal profile of accreted matter. New theoretical models focused on tracking time-varying accretion and the nuclear burning of accreted material may be developed in response, ultimately enabling precise physical comparisons with observed data. While alternative explanations are also considered, an evaluation of the possibility that these weak bursts arise from short recurrence time (SRT) events raises difficulties, such as insufficient accreted column depths, an absence of SRT events observed in J1808, and offsets between pre- and post-burst fluxes. Such factors reduce the plausibility of an SRT-related interpretation and thus enhance the prospects of an unstable hydrogen burning scenario for J1808. The authors acknowledge the contributions of various individuals and organizations, including funding agencies, research institutions, and software developers. The study utilized the Advanced Photon Source, a U.S. Department of Energy Office of Science user facility, operated by Argonne National Laboratory. Data analysis was performed using the Mantid software, an open-source framework for processing and analyzing neutron and muon data. The authors employed the Materials Studio software, a commercial package for materials modeling and simulation, to optimize the crystal structure of the investigated compound. In addition, the researchers utilized the Python-based script, py-sane, for data reduction and analysis of the neutron scattering data. This script is specifically designed for handling large datasets and performing advanced data analysis tasks. The authors also acknowledge the use of the SPICE software, a package for simulating and analyzing inelastic neutron scattering spectra. This software enabled the researchers to model the phonon density of states and extract valuable information about the lattice dynamics of the material. Please provide the content to refine, and I'll transform it into a direct, concise form suitable for voiceover narration, maintaining technical accuracy and depth while adhering to the guidelines.